We'll continue with the simple double pendulum that we began in the last screencast and calculate the equations of motion now. And to do this, we need to say that these are now masses instead of just particles. So it's mass P located at point P and the mass Q located at point Q. We've already determined the accelerations as observed in the inertial reference frame of each of these masses. And so now we apply Newton's second law, so F equals ma to both masses. And so this would state that all the forces applied to point P are equal to the mass of point P multiplied by the acceleration of P as observed in the inertial reference frame. And then the second inertial equation is all the forces applied to point Q, or mass Q, is equal to the mass multiplied times the acceleration of that point in the inertial reference frame. We have our mass and acceleration for each of these points, so we need to determine what the forces are that are applied to each of the masses. And to do this, we use a free body diagram for each mass. Starting with mass P, our free body diagram is simply a point, and all the forces that are applied to this point, we're going to have gravity that's operating in the E1 direction. So this will be the force due to gravity, which is the mass of P multiplied times gravity in the E1 direction. And then there are two forces that are applied in the links of these double pendulum. So the force along OP and a force along PQ. So we'll call the force along OP F1, and it's operating, or you see that its direction is going to be in the negative A1 direction. So it's negative F1 A1, and then force 2 along link 2 will operate in the positive B1 direction. And so a reminder about all the forces that are applied to a free body diagram, these should all be written as vectors. So we have a direction, we have a scalar, which is F1 in the negative A1 direction, F2 in the B1 direction, and then the force due to gravity, which is in the E1 direction. And we'll have a similar process for mass Q, in which our free body diagram is a point, and on this point we need to have the force due to gravity, which is operating in the E1 direction. So the mass of Q multiplied times G in the E1 direction, and then the only force applied to this will be the F2, and it needs to be equal and opposite of how we've drawn it on this free body diagram for mass P. And so this will be F2 in the negative B1 direction. We add up all these vectors to get the force on point P, and so this is negative F1 in the A1 direction plus F2 in the B1 direction plus the mass of point P multiplied times G in the E1 direction, and then for all the forces applied to mass Q, this is negative F2 in the B1 direction plus the mass Q multiplied times G in the E1 direction. We apply Newton's second law to mass P, and so the force on the left hand side and then mass times acceleration on the right hand side, and so we get negative F1 in the A1 direction plus F2 in the B1 direction plus the force due to gravity in the E1 direction is equal to the mass of point P multiplied times the acceleration, which is L1 theta double dot in the A2 direction minus L1 theta dot squared in the A1 direction. Now notice we have a vector equation that's in a mixed basis. We have everything, our A basis, our B basis, and our inertial basis, and on the right hand side we put this all in the A basis. So convert all this on the left hand side to the A basis, We do this using the transformation tables that we developed when applying the reference frames to the system, and then determine or equate your coefficients from your A1 basis, or from your A1 direction, and your A2 direction. After we've equated our coefficients, we now have two scalar equations. We have three unknowns though. We have theta double dot, which we're solving for. This will be the equation of motion for that first degree of freedom theta. And then we still have two other unknowns, which are the force in the first link and the force in the second link. So this means that we need to apply Newton's second law to the second mass, mass Q, using the same procedure, and we'll be able to solve for this force 2, as well as theta double dot and beta double dot are going to show up in those equations. So the left-hand side, when we apply Newton's second law to mass Q, will be all the forces on mass Q. We've already solved for this, so this is negative F2 in the B1 direction, plus mq multiplied times g, force due to gravity, in the E1 direction. And this is equal to the mass of Q multiplied by the acceleration expressions. And you'll notice a couple things about this expression. Is on the left-hand side, it's a simpler expression because we only have one force, that's a constraint force, the F2, that we expected. But our right-hand side is much more complicated because we're further out from the inertial point. And in this, we have both a theta double dot and a beta double dot in our expressions. And so we'll transform B1 into the A basis and E1 into the A basis, and then equate our coefficients. And so now we have four scalar equations and four unknowns. Our unknowns are F1, F2, theta double dot, and beta double dot. And after some substantial algebra, we solve for theta double dot and beta double dot to get the two equations of motion for the system. So you can see immediately that these two equations of motion that we have for theta, degree of freedom, and the beta degree of freedom are not pretty. So I highly encourage you to check your algebra with a software package that has a symbolic solver such as MATLAB or Mathematica or MathCAD, and there are several options for this. But now that we have our equations of motion, you can see a couple things. First is that we have our simple pendulum equation that's embedded in both of these equations for theta and for the beta degree of freedom. And with all this algebra now out of the way, you can implement this now into a numerical differential equation solver and experiment with different initial conditions to see how the system behaves. This double pendulum, or simple double pendulum, is really interesting because it has interesting chaotic behavior with some initial conditions, and it's a highly nonlinear system, so it's fun to play around with numerically speaking. But as a quick recap, before we got to the nasty algebra at the end, it was a relatively simple procedure that we've done before multiple times. The only difference now is that we use rotating reference frames and adding of our angular velocities of our reference frames with respect to each other to find the acceleration. And then we simply use Newton's second law, F equals ma, and apply it to both masses.